The question here says the velocity v of streamline flow of a liquid depends on density, radius, and viscosity. Okay, so we represent out an equation. Velocity depends on density, radius r, and viscosity. Now, the extent to which it depends on these parameters were not given. So we represent that with an unknown. So we say velocity depends on density to an exponent of x, radius to an exponent of y, and viscosity to an exponent of z. Derive an expression connecting them. So we are to derive an expression connecting them. How do we do that? We are going to use dimension analysis for that. So let's write the dimension of each of the parameters. The dimension for velocity is Lt to the power of -1. Dimension of density is mL to the power of -3. That is mass over volume. Dimension for radius is L. Dimension for coefficient of viscosity is mL to the power of -1, T to the power of -1. If you do not know how this is so, I recommend that you check our previous videos. We have covered things like this in previous videos. Now, going forward, we have an expression here. So let's change that expression to an equation, which means we change this variation sign to an equal to. So this is going to equal to V velocity equal to K density to the power of x, radius to the power of y, and coefficient of viscosity power of z. Let's go ahead and substitute the dimension of each parameters into them. So this is going to equal to Lt to the power of -1 equal to K. Dimension for density is mL to the power of -3. So we have an exponent of x, so multiply all through by x. Multiply by dimension for radius is L, so L to the power of y. Multiply by dimension for coefficient of viscosity is mL to the power of -1, T to the power of -1, all multiplied by z. Now, we are going to multiply the exponent all through. So we have Lt to the power of -1 equal to K. The exponent of m here is 1, so 1 times x is going to give us m to the power of x multiplied by L to the power of -3x times L to the power of y multiplied by m to the power of z, L to the power of -z, t to the power of -z. The next thing we do is combine similar terms. So we have Lt to the power of -1 equal K m to the power of, we have exponent of x here, we have exponent of z here for m. So x times z in indices is going to be addition. So we have x plus z. And for L, we have L to the power of -3x plus y minus z. And for t, we have t to the power of -z. We have only one t. Next thing we do is compare the left-hand side and the right-hand side. On the left, we have only L and T as the only parameters. On the right-hand side, we have M, L, and T. So you can see that on the left-hand side, we do not have M. Whenever an exponent or whenever a parameter is missing, what you do is you give that parameter an exponent of 0. That is, we put M to the power of 0 on the left-hand side. So on this side, we write M to the power of 0. We have not changed this equation at all because m to the power of 0 is 1. So if we multiply the left-hand side by 1, we're still going to have the same thing. So we've not done anything. We only introduce m so that we can have similar parameters on the left and the right. Going forward, the next thing we'll do is compare each of the parameters on both sides. So comparing for m, we have m to the power of 0 equal m to the power of x plus z, right? So m cancel m, means 0 equal x plus z, which can mean same thing as x equal negative z. So we make this our first equation. This is equal to equation 1 because you cannot solve further from here. And the next thing we do is compare for L. So comparing L on both sides. On the left hand side, we have L to the power of 1 equal to L to the power of negative 3x plus y minus z. Right? Now, L cancel L. We have 1 equal negative 3x plus y minus z. I'll just leave this way to make things simpler. So let's call this equation 2. Now, the next thing is compare the last one, which is t. Comparing t on both sides, we are going to have, on the left hand side, we have t to the power of negative 1. On the right hand side, we have t to the power of negative z. So t cancel t, negative 1 equal negative z. Negative cancel negative, so z is equal to 1. So we found c, so z is equal to 1. Now from equation 1, we have x equal negative z. Since z is 1, it means that x equal negative 1 from equation 1. So x equal to negative 1. The last thing we look for now is z. Sorry, y, I mean. Now we can use equation 2 to find y. Equation 2 says 1 equal negative 3x plus y minus z, right? So 1 equal to negative 3, x is negative 1, so negative 1 plus y minus z, z is 1. So this is going to give us 1 equal negative 3 times negative 1 is 3 minus 1 plus y. So 1 equal 3 minus 1 is 2 plus y. Subtract 2 from both sides. We have y equal 1 minus 2. And 1 minus 2 is negative 1. So y is equal to negative 1. All right, so now let's substitute that in the equation. Clear some space so that we can substitute in the equation. So substituting into this equation, we have v equal to k. Density as an exponent of x, and x is negative 1. So this is equal to negative 1. Radius as exponent of y, and y is equal to negative 1. So this is equal to negative 1. Then viscosity as exponent of z, z is 1. So this is equal to the power of 1. Now we have v equal k. When we have a negative exponent, this is the same thing as 1 over density multiplied by 1 over radius multiplied by coefficient of viscosity. So putting it together, we have k equal to v equal to k multiplied by viscosity over density times radius. So the formula for connecting each of the parameters is this, and this is the formula for calculating streamline flow of a liquid.